All right, the last section we're going to look at is on period changes. So it's the last transformation for sine and cosine. So let's just take a quick look at the ones we've already done. Okay, so we've done phase shift. We've done amplitude change. And we've done vertical shift. Okay. Anytime you do shifting, whether it's phase shift or vertical shift, it always involves one of two operations. What operations are always involved with shifting? Check. What operations? So what arithmetic operations? Not trig operation, just simple arithmetic. So it's four simple arithmetic. Two of them are involved with shifting. Yep. Yes, so anytime you add or subtract, it's always a shift. Which shift is it? Well, depends on where you do it. When you have a phase shift, where is the adding or subtracting? Yeah? In the parentheses. Here's an example. Sine of x plus pi over 2. That's a phase shift because you added inside the parentheses. So that's left and right. Okay, so this is phase shift. Let's put left, right. So vertical means up or down. So up, down. Since it's a shift, it's still going to be adding or subtracting. But where is the adding or subtracting for a vertical shift? Where is it? Outside, yeah, outside the parentheses. So an example of that would be like y equals cosine x plus 2. There are no parentheses grouping the x and the 2. Even if you put parentheses around the x, that makes no difference. It's got to be around the x and the 2 to be a phase shift. So questions between the two shifts. They're both adding and subtracting, it's just where. One's inside, one's outside the parentheses. Now, amplitude change. That wasn't adding and subtracting. What operation did that involve? Multiplication. Now, the one we do today, which is a period change, and the one we did yesterday, amplitude change, are both multiplication. Does anybody remember for multiplication, for yesterday, where was the multiplication? In where? Before it. Definitely wasn't right next to the x. It was out in front. So you had something like 3 cosine x. That's an amplitude change. You multiplied, but it's out in front. Today we're going to do multiplying, but where do you think the multiplication is going to be today?
In front of the x.
Right in front of the x. It's going to be inside with the x. So that's the question. Is it with the x or not with the x? That's what makes the difference. So now I'll show you period change.
So what changes is like, what kind of changes amplitude change?
Amplitude? What is amplitude? When you change the amplitude, what axis does that affect? It affects the y's. Right? So this is this affects the graph on the y-axis. It stretches or compresses it. So here's an example. Here's an original. There's an amplitude change. Okay? Notice no change in the width at all. If you took a ruler and measured from here to here on the small one, or from here to here on the big one, they have exactly the same width, but they don't have the same height. Okay? They don't have the same, we call it amplitude. Okay. So that might be handy for a reference sheet, just to kind of summarize them. So now let's look at a period change. Okay, so we already know it's going to be multiplication, and we already said where it's going to be. It's going to be inside, next to the x. So the letter that your book uses, you can use a different letter if you want. I'm just matching it up with the book. They use the Greek letter omega. Looks kind of like a W. But omega just stands for a number in front of x. So it could be like sine 4x. Could be cosine 2x. could be sine of 1/2 x. The important thing to remember is you are multiplying, and it is inside the parentheses. So anytime you get stuck, those are the two questions you want to ask yourself. What operation is it? Is it adding or subtracting? If it is, okay, it's a shift. Where is it? Is it inside or outside? If it's inside parentheses, like today, that's a period change. Outside, amplitude. Okay, so any questions on what a period change looks like? Just a number times x. Now, another important question is going to be, is the number bigger than 1 or less than 1? That's going to control whether it does one thing or the other. Now, with amplitude change, when you put in a bigger number, what happened to the graph? It stretched. Bigger number made it bigger. A fraction. If you put in like 1/3 in front, it would make it smaller. So this one does exactly what you would expect. Bigger number makes it bigger. Smaller number makes it smaller. How about vertical shift? When you do plus, which way did it go? Well, vertical.
Oh.
So which way? Up. So when you do vertical, plus is up, minus is down. Is that what you would expect, or is that kind of weird? That's what I would expect, right? Usually positive numbers go up, negative numbers go down. So amplitude change and vertical shift they're like the normal ones. Now, phase shift, we had to do the opposite. This was one of the two we had to do opposite. When you see plus, which way does plus actually shift it? Which way? Minus?
Well, it goes from a positive to a minus.
Okay, so you do the opposite, so which way does it move?
The other way.
Left. So if you see plus, it actually goes left. If you see minus, it goes right. That, to me, that's the opposite of what you would expect. All right? But that's the way phase shift works. It does the opposite. Same thing's going to happen here. Period change is going to do the opposite. So when you put a big number in front of x, what do you think is going to happen? Is it going to stretch it bigger or compress it smaller? Yeah, it does compress it. So let me show you. Here's sine of x. Here's sine of 4x. So let's graph it. That's the original. And there's when you put in 4x. So it compressed it a lot. And we can actually, if I make it bigger, it's easier to see how much it compressed it. So let's go like this. Look at one section in blue. Right? One section would be from like here to here. That's one full cycle in blue. Can anybody tell how many cycles in red it makes between those two green lines? It's one blue. How many red? 4. Yeah, that's because we put a 4 in front. It basically took the graph in blue and it compressed it 4 times as much. So you can kind of think of it, it's going up and down 4 times as fast. Let's see. So if we put a 4 in front, it compressed it. What do you think would happen if I did 0.5? Yeah, it's gonna stretch it out. So there's the original, and now the one you're gonna see in red is gonna be much more stretched out. Okay, it's much longer. We call that the wavelength. It has a much longer wavelength versus the one I drew on the board over here. We've got a shorter wavelength. Longer, shorter. We'll talk about what that means in terms of sound when you change the wavelength. All right, let's go back. Go back here. So as I just showed you on the calculator, period change compresses or stretches the graph on the x-axis. Now, we've never changed the period of the graph before. We've never changed the width. We've shifted up and down. That doesn't change the width. We've stretched up and down. That changes the height. It doesn't change the width. And we've shifted left and right. That doesn't change the width. If I take that line and I shift it over here, left or right, it still has the same width. It's just in a different spot. If I move it up, it still has the same width. It's just in a different spot. And if I don't think I can stretch that. I'm not sure. Yeah. So if I stretch it down, looks kind of weird, but it still has the same width. It's just been stretched. But if I measured left to right, it's exactly the same as what it is right there. Okay? All right. So the two things we just mentioned. If the number in front is bigger than 1, it compresses. The bigger the number, the more it compresses. So if you were to graph like 20x, I think I did 4x, but if you did like 20, it would compress it 20 times as much. Eventually, you compress it so much you can't even see the graph. It's just too squished to even see it. Right? Like if you did something like, let's just try 20x. So for every cycle in blue, you're going to get 20 in red in the same space. So you can't even really see it. It's all squished together. Bigger the number, the more it compresses. If you put a number between 0 and 1, like 0.5, which is the same as I have, or 1/3, 1/5, 2/3, any number that's less than 1, it's going to stretch it. The smaller the number, the more stretch you get. So if you graph like 1/10 versus 1/2, 1/10 is a much smaller number than a half. 1/10 is going to stretch it even more. So the closer you get to 0, the more stretch you get. We're never going to have a negative. You could. Negatives, what did we learn yesterday? When you put a negative, it causes the graph to do what? Flip. So yesterday it flipped up to down. If you put a negative today, it would flip left to right. Okay, it would flip that way. But we're not going to look at that. Okay. Any questions on that? All right, so we did that, and I did that. Okay. So before I keep going, I just want to kind of talk a little bit about what this would sound like. So when we had this, we did this yesterday. What was the difference between those two sounds? If each wave in black represented a sound, how would you have heard the difference? Yep.
No, one was louder.
Yes. The one that's stretched out more is louder. So today, we're not stretching it up and down. We're stretching it left and right. So we're not going to be changing the volume. What do you think stretching left and right would change? Right?
Like, so kind of like the sound, I guess. Or
I'm not sure. What do you mean by the length of the sound?
I mean, like how long it actually like carries out for.
So that's going to be controlled basically by when I hit start and stop. So when I turn it on and when I turn it off, that's what will control how long you hear it for. But it's going to control something else. But it's a good guess, yeah?
How deep and how high it sounds?
Yeah, it's going to change the pitch. So we'll change the frequency of the sound. And actually, since you came in, I've been playing a sound, but nobody said anything. So I'm guessing, because if you heard it, you probably wouldn't like it. It's a very high-pitched sound, extremely high. It would be very irritating.
As soon as you mentioned it, I heard it.
As soon as I mentioned it, you heard it? What if I said I'm not actually playing any sound? It's just no, I am playing a sound. I can prove to you I'm playing it. Even though you can't hear it, I can show you that it's in the room on an oscilloscope. So right now, you're seeing all kinds of frequencies because I won't stop talking. But once I stop, and you can kind of see it, there's one frequency way over at the right-hand side that's spiked very high. And that's because there's a sound in the room being picked up by the microphone. So I'll stop talking, and you'll see the number right here, the main frequency, probably say about 19 kilohertz. So I don't know if you saw it, but it said 19.2 kilohertz, because that's exactly the frequency that I've been playing the whole time. 19,200 hertz. You can feel it?
Dance magic.
Huh.
Feel it.
Well, I'll play some sounds that you'll definitely be able to feel more. Usually high pitch, after a certain point, you don't hear it. And just to prove that I really am playing it, watch what happens once I press stop. You'll see that spike over at 19,000 disappear. It's gone. So I'm still talking, you still see all the other sounds, and if I turn it back on, all of a sudden there's the spike again because there is a sound being picked up by the microphone. So let me back it down a little bit. And you'll probably be able to hear this. So this is going to be much lower. I mean, it's still going to sound kind of high pitched, but it's much lower. And you're going to see a spike at around 3,200 now. Okay, so right around in there, it'll spike up. There's also some other spikes. I'm not really sure what those are. Just like some echo or something. I'm not really sure, but the main one, and it says the main frequency that it also picks up. 3.22. It's exactly what I just played. 3,220. It's just kilohertz versus hertz. And everybody hear that? Yeah, that's pretty. If you can't hear that, then you probably don't hear me talk. Maybe that's good. I don't know. So now let's play 7,000 hertz. A little bit higher, so now you're going to see maybe a line right in there somewhere. Okay. So, and again, if you looked at the main frequency, it said 7.001. It can actually hear that 0.001, because if I bring it down to 7,000 and now play it, watch, it won't say 7.001. It'll actually, the microphone will only hear the 7,000. 7.00000. So that 1 hertz, like I can't hear the difference. I don't think anyone can really hear it, but the microphone actually does hear that 1/1000th of a kilohertz difference between 7,000 and 7,001. Right, so let's jump up to, it's about 13.19 kilohertz, or 13,000 hertz. 13,195. Okay. Anybody that can't hear that one? I had someone in the other class that couldn't hear it. They lost it at that point, but I can still hear it. As it gets higher, you need to go a little louder because higher sounds are just harder to hear. Can you hear that one? So very, very high.
I felt that one.
A little harder to hear. Let's just bring the volume up a little. Notice how compressed the wave is. It just makes that fancy little color pattern. That's really nothing. It's just compressed a lot. Right, let's try about a little over 16,000 kilohertz.
I can barely hear.
Now that one I lost, but I know it's here because I saw it. And the frequency said 16.342. Anyone that couldn't hear that one?
I could just barely.
Just
hear
barely?
it.
All right, so if we go a little more, then this will probably be beyond.
I don't hear anything.
It's gone. Yeah.
Hearing damage.
I can barely hear it.
You hear crackling?
Yeah.
That's just weirdness. That's not really the sound. That's not the sound. So that's a very high 19.7.
Can you lower it really slowly?
It won't really make a difference, no. If you can't hear, yeah, it's pretty loud. I have, because if I bring it down, listen to how loud of a sound I'm playing. I mean, that's pretty loud enough you can hear it. It's just high pitch, you just can't hear it. So, if we go up, I'll just go up slowly. At some point, people are probably losing it.
I just lost it.
I lost it at like
It stopped at like 16.5, like 1.5.
All right, now on the other, kind of on the other end, what I can do is I can play a lower sound, and eventually what happens is the sound kind of goes from coming out there to more coming out of that speaker. Because the way the sound works is the frequencies are split up between the subwoofer and the soundbar. So the subwoofer starts to handle the frequencies when they get under about 100. So it's easier if I can type it in though, so I can type it in exactly. So let me type it in. And the lowest that I can go is about 45. So that's the lowest frequency that I can play. Any lower, and that speaker won't be able to play it. But you'll get the idea of what 45 sounds like. So let's turn it up a little. And here's 45. So that's 45 hertz.
Oh, it's really louder on speaker, yeah.
What's that?
It sounds like when you're at the concert and you're near the speaker.
Just a lot of bass, yeah. So depending on where you're sitting, it may sound louder or softer. But if you listen to it, when I play 45 hertz, that's pretty much all you hear. Right? I didn't really hear anything else, but watch what happens if I start to turn it up, the frequency. Different objects resonate, which means they vibrate when different frequencies are played. So as I get a little higher, somewhere around 48 or 50 hertz, you're going to hear different things in the room start vibrating. I assure you nothing will fall, and you'll be okay.
We need a couple water.
I like it.
But you're going to...
Oh, we need a couple water.
Oh, yeah.
You might see it, yeah. So let me play it and turn the frequency up slowly, and all of a sudden you'll definitely hear when something happens. So just between 50, stopped. So what's happening is that's not my speaker freaking out. That's actually, maybe it's a light bulb or something is vibrating, because that's just the frequency it vibrates at. So if you had like a, I don't have like a glass with me, but if you had a glass that you just put on the table and you just kind of, just flick it like that, you'd hear that ping kind of sound. Well, if you did that right near this microphone, you could see the frequency that the glass made that sound at. And then if you played that frequency extremely loud, that's the frequency that the glass vibrates at, so that frequency would break it. Now, it wouldn't break like all the glass at the same time. In fact, it wouldn't do anything to the windows because the windows are held in place. That's kind of like if you put a glass down and just had your friend put their hands around it and then you hit it with your finger, well, it won't make any sound because they're holding it, so the glass can't move. That's like the glass in the door, the glass in the windows. That glass is held in on all the edges, so it can't vibrate and crack. But if you had a glass, you could do that, and it would crack. And you can go on YouTube. People do it with their voice, but you have to be able to like sing at just the right frequency, very, very loud, and hold it. You can't your voice can't change. It has to really keep the same frequency. Which, if you're a professional singer, maybe you can do that. So, right. Any questions on that? Let's just do this one more.
Do it again.
And now it kind of stopped the vibrating, whatever was vibrating in the light, at least near me, it stopped. As you continue, you might be able to find something else that vibrates, but
Can we continue?
eventually most objects in this room, they're not going to vibrate much above a couple hundred hertz. Then we're getting into the sounds again that you hear more than feel. Like you might be able to feel that, I don't know. But yeah.
What frequency do humans vibrate at?
Everybody's different.
What would break me?
I don't know, you might...
Check.
The other thing is humans aren't really, like, there's a lot of soft stuff. And when you have soft, it doesn't vibrate as well as something that's hard, like glass. Like glass is solid.
Okay.
Glass can break. Yeah. But you might, like, if you get it just right, maybe you would feel it like in your teeth or something, vibrating. If you got it just right, I don't know. But again, everyone's teeth are different, and your teeth, you know, if you were pushing on your teeth with your tongue, that would change it because then you're holding your teeth in place. I don't know. So yeah, it might be a little different. Your glasses, you might feel your glasses vibrate because those are hard and they have glass in them, so you could like feel them. You probably feel like it's tickling you or something, just vibrating real fast. But again, glasses have frames most of the time, so they're held in place. But yeah, it's all kinds of different things. All right, so you kind of heard what happens when you stretch and compress. It changes the frequency. Now, normally, if you don't stretch or compress it, and you just leave it with the original, does anybody remember the width from here to here? It was measured in degrees. 360. So normally you have to go through 360 degrees to do a full cycle. Well, now we're changing it. So what we want to be able to figure out is, how much did you change it? Is it more? Did you stretch it out? Or is it less? And this is the formula that you use to find the width of a cycle. Did your cycle get wider or did it get narrower? Okay, what happened? This formula will tell you. So the calculation is always 2 pi, that's the original cycle, divided by omega. Okay, omega is just the number that's in front of x. 4, 2, 1/2. Okay? So whatever number is in front of x. So let's look at an example. This is another type of question you'll see on the test that there is no graphing required. The answer here is a number. That's it. Okay. So I want to find the period of this. Okay. We're going to graph it later. But for now, all I want to know is, okay, if I measured from here to here, how long would it be in radians? You can do degrees too, but we usually do radians. That's what this formula will tell you. So any question on what the formula tells you? It's the width of a cycle. All right, so now if we want to figure it out, start with your fraction. T equals, you always put 2 pi in the top. The number in the bottom changes for every problem. What's the number that would go in the bottom of this one? 2. And then you always reduce as much as you can. So the final answer would be pi. What's the length of it originally before you mess with it? 360, or what's that in radians? 2 pi. So your normal graph is 2 pi. This graph is 1 pi. So you shortened it. You shorten the amount of time it takes to go through a full cycle. How much did you shorten it? You actually made it half as short. Right? So any question on that number? That number is going to be important when we do graphing in a minute. But for now, I just want to find that number. All right, how about cosine 5x? Set up your fraction. What always goes in the top? 2 pi. And what goes in the bottom this time? 5. So what you've done this time is you've actually taken 2 pi and compressed it by a factor of 5. So your graph now is 5. Basically, it's going to be compressed 5 times as much. Does that mean it would be like 5 times as high of a pitch? I'm not really sure exactly. It would be higher pitch. I don't know if it would be 5 times higher. I'm not even sure what that really means. If you say, oh, that sound is twice as high pitch as that one. I don't know. Does that just mean the frequency is double? 400 to 800? I'm not exactly sure. I have to check. Any question on number? So both of these compressed. That's a number smaller than 2 pi. That's a number way smaller than 2 pi. It's 1/5 of 2 pi. Now, let's look at this one. I said that when you multiply by a fraction, what happens when you put a fraction in front of it? Yeah? It expands, it stretches. So when we do this one, I'm going to expect a number much bigger than 2 pi. Right? It's going to stretch out. So it's going to take longer to do a cycle. Okay, how long? Well, let's see. Okay, so what goes in the top? 2 pi. And what would go in the bottom? 1/4. So when you want to divide by a fraction, we usually don't think of it as dividing by a fraction. How do you do that? You could, let's just say like somebody doesn't quite, they're not good with decimals. We don't even need decimals. How do you divide by a fraction? You don't really divide, you switch it. You multiply by the reciprocal. What does that mean?
Flip it.
Yeah, we just flip it, right? So make it 4/1. The top stays the same. Now the top wasn't a fraction, but you could make it 1 if you want. How can you make 2 pi a fraction? Just put it over 1. So instead of 2 pi divided by 1/4, make it 2 pi times 4. And what does that give me? 8 pi. That's definitely bigger than 2 pi. How much bigger? It's 4 times as big. So that's stretched out. It'd be a lower frequency sound. Okay. Any question on that? Okay, so that's how you find the period. Right? So just to kind of draw it visually, you just found this point right here. You're telling me how long it is to get to the end of the cycle. In this case, it's 8 pi. In that case, it was 2 pi over 5. And I think the one before it was like pi, I think. All right. So that's important because this formula tells you where the cycle ends. Now we got to figure out, where does it begin? Where's the middle? Where's the high and the low point? If we can figure all 5 of those out, then we can sketch a period change. Okay. So, one of those points we just figured out. We'll come back to it. I want to start with the figuring out which column stays the same. Think about what we're doing. We're stretching left and right. So what values are not affected at all? The y's. Nothing happens to the y's. So now you copy the y's down from the original table. How do you know what original table to use? Well, if the graph says sine, use the table that has sine. If the graph says cosine, use the table that has cosine. Okay, you should have both tables in your notes for Monday. So now, if the y's stay the same, the x's are going to change. Whether you look at the table for sine or cosine, what is the first x value? 0. So now, let's think about what happens if we take 0 and stretch it out 3 times as much. We triple it. What do you get if you triple 0? You still have 0. All right? Now let's think about if we compress it. Let's take half of 0. How much is that? It's still 0. So basically, if the first x coordinate started at 0, no matter how much you stretch or compress the number 0, it's always 0. So your starting point for every period change is always 0. No matter what. All right, so we just figured out this. Now we want to figure out where it ends, just because that's the easiest way to do it. Get the beginning and get the end first, and then everything else is in the middle. We just talked about how to get the end. There's a formula you use that tells you how far away the end is. How far away is one cycle? What is that formula? Yep. So the 5th coordinate, which is the one at the end of the cycle. So all you got to do is figure out how far away is the end of the cycle. We already got a way to do that. Do 2 pi over omega. And that'll tell you where your cycle ends. Once you know where it starts and where it stops, the rest is pretty easy. Okay, so when we've set up our axes all week, I've said to you there's lots of different ways you can set up your axis as long as you are what? When you label an axis, you just have to make sure what? Evenly spaced, that it's consistent, right? So every point that you pick has to be evenly spaced. They all have to be consistent. So this one, that's right in the middle, fits that definition. It's exactly halfway between the beginning and the end. So think about if you had two test grades, right? You had like a 70 and an 80. And you wanted to know the one right in the middle. It's very easy to do a quick calculation to get the number in the middle. What's the name of that calculation if you know two numbers and you want the one in the middle? The what? So the median would, yes, if you had a set of numbers in order from lowest to highest, it does give you the number in the middle. What about like if I was doing your grade at the end of the term? Like if you had test grades of like 50, 60, 70, and 80. How do I get your grade? The mean, right? Or some people just call it the average, right? So if you want to get this one, all you have to do is average the first and the fifth. So the third x-coordinate is the average of the first and the fifth. But what is the first one? What number is always the first one? And it's super easy to average a number with 0. If you want to average a number with 0, what do you really just have to do? Like if you have two numbers and you want to average them, one of them is a 0. Just divide it by 2, right? So if you got, very simple, if you got 100 and then you didn't take the next test and I had to get your average. Well, you have two tests and you got 100 on one and 0 on the other, 50. Right? All I have to do is take your average and cut it in half. If I want to average it with a 0. Two numbers, average with 0. Okay, so the third x-coordinate is the average of the first and the fifth. How about the second one? In order to make sure that that's nicely spaced, what do you think it's going to be? Yeah? Yeah, if you average it with the first and the third, it's going to give you one that's exactly in the middle. That's what you want. You want everything perfectly in the middle, nicely spaced. So the second x-coordinate is the average of the first and the third. Okay, and the last coordinate we need to find is the fourth. I'll just draw it again. How do you think you would get the fourth coordinate so that it's exactly in the middle of everything else you already have? Yeah, just average the third and the fifth. Now, this idea of averaging, it's not always the fastest way to do it. There's different ways to do it depending on your numbers that could be faster. But I think it's going to be more confusing if I show you like 2 or 3 ways you can do it. Even if some of the ways are faster for other problems, it's just going to be more stuff to try to remember. So this works all the time. Okay. Whether or not it's the fastest way, it just depends on the numbers in the problem. Okay. Just think of like numbers in real life if you wanted to average them. Like if you wanted to average 6 and 10, that's easy. 8 is a number that's right in the middle. If you wanted to average 6 and 11, that's not as easy. You don't get a nice answer just because the numbers aren't as nice. Okay, so now we'll actually go through and we'll do a couple graphs. Okay, so just remember we do it in that order. Get the beginning and the end, and then everything else is just average. What's in the middle of everything else. Okay, so let's try graphing sine 2x. You don't have to do it this way, but usually what I do is just get the column that stays the same out of the way. Just get that done. All right. So what column is going to stay the same?
The y.
Yes, the y's are going to stay the same. How do you know that?
So you said the x's are changing because they're compressing.
Okay, how do you know that this is the type of graph where that's actually happening though?
Multiplication.
Yep, so that's part of it. There's multiplication. Where is it?
It's next to the function.
It's next to
The x.
the x. So when the number is next to the x, that's how you know it's a period of change. And he already said it was multiplication. So those are the two things. Multiplication inside with the x. If you want to think of it as parentheses, that's the same problem. It's right grouped in with the x. Okay, so y's stay the same. What are my y values for sine? Yep.
0, 1, 0, -1, 0.
Yep. So you have 5 points for those. And now the first x value, this one should actually be very easy for this one because it's always what? 0. 6 points. Alright, so now we know where the graph starts. Starts right at the origin, so I could actually put that if I wanted. But I'll finish graphing it later. Now I want to figure out where it ends. So what is the formula that tells me where the cycle ends? And in this case, it's going to be 2 pi over 2. So where does this graph end? Pi. Yep. It ends at pi. Now everything else is just averaging. So let's get what's right in the middle. That's the third one. So to average two numbers, what do you do with them again? Add them up and divide by 2. So add them up. And now dividing by 2, is that the same as just taking half of them? It's the same. I'm just going to write it that way. So add them up and then just take half. Or divide by 2. Same thing. What's 0 plus pi? Pi. And then what's half of pi? Pi over 2. So there's your third. And now we're going to average 2 more times to get the second and get the fourth. Okay? Let's do the second. So we're going to add them up and then take half. So we got 0 and pi over 2. What's 0 plus pi over 2? Pi over 2. And what's half of pi over 2? You just multiply straight across. 1 times pi is pi. 2 times 2 is 4. Now, if you write everything, I'm going to do it off to the side because this is not part of the answer, but if you write everything with a denominator of 4, you would see a pattern. The first one is 0 pi over 4. The next one is 1 pi over 4. That's really 2 pi over 4. And what would the last one be? That's 4 pi over 4.
So 3 pi over 4.
So this one should be 3 pi over 4. Okay. I'll do the averaging to show you that's what it comes out to, but that is the pattern. 0 pi over 4, 1 pi over 4, 2 pi, 3 pi, 4 pi. All over 4.
Is that always or just for this one?
There's always a pattern.
No.
Whether or not it's always over 4 depends on the problem. If this was a 3x instead, you wouldn't have 4s here. You'd have another pattern, but it wouldn't be this one. Okay, so let's find this pretending like we didn't see the pattern. We would take pi over 2 and pi and average them. All right, so let's take pi over 2 plus pi over 1. Add them up and then take half. Now, we can't add these right away because we're missing what? We don't have the common denominator. What is the common denominator between a 1 and a 2? 2. So if you double the bottom, you also have to double the top. So now we can add them up. Denominator is 2. What's 1 pi plus 2 pi? 3 pi over 2. And now multiply straight across. 1 times 3 pi, 2 times 2. So it's a lot faster if you see the pattern, but if you don't, you can still do it. Questions on the table? As far as the ones we do, arithmetic-wise, that's the worst one we have. So if you can do that one, the next two are easier. Okay. Now, since all of these are averaged, that's how we got them, they're all nicely spaced. In degrees, that's 0, 45, 90, 135, 180. They're all 45 apart. Okay? Since they're all nicely spaced, that means you can use them for your labels. Okay, so let's put those as our labels. 0, pi over 4, pi over 2, 3 pi over 4, and pi. Now, when you reduce them like that, it doesn't look like there's a pattern. But remember what it looked like if you don't reduce them. Nice pattern. 0, 1, 2, 3, 4. Nicely spaced. Okay. If you reduce them, that's fine. Now, you can label your graph with reduced values, or you can leave them not reduced. It doesn't matter. One thing you don't have to worry about today is the y-axis. It's always 1 and -1. Every problem. Okay, so we start at the origin. We go up to 1, 0, -1, back to 0. I got an extra mark there I don't need. That might happen on the test too. Just don't use it. There's my graph. Now, technically that graph should look compressed because we had a number bigger than 1 in front. To me, that looks like every graph we've done all week. It doesn't look compressed at all. How come? Because I changed my labels, I changed my scale. If you change your scale, you're not going to be able to tell that it's been stretched or compressed. But that's the easiest way to graph. Okay. Any questions on that one?
So on the test, are we going to have the same scale for the original?
Nope, on the test, all I care about is the final graph. Yep, you're not going to have to sketch the original. That's all I would look for on the test. This graph, that table. Okay, let's look at this one. Same transformation as last time. I see multiplication. Where is it? Inside parentheses next to x. So we just talked about which ones stayed the same. It's the y's. But now we're doing cosine. Can someone tell me what my y's are for cosine?
1, 0, -1, 0.
Yep, 1, 0, -1, 0, 1. First x value for every period change. Yep, it's always going to be 0. Now, if you think, is it 0 like for every single period change in the entire world? No. Not if I combine it with a phase shift, right? So if I were to shift it and then stretch it, that's doing two things at the same time. Now that's different. We're never doing two things at the same time, which is why this trick works. But if you start like shifting and stretching together, it changes a little bit. All right. So the cycle begins at 0. I need to know where the cycle ends. What's going to be my fraction that tells me where the cycle ends?
2 pi over a quarter.
Yep, 2 pi over a quarter. We just did this. Where did the cycle end when we did that? 8 pi. So now I know the cycle ends at 8 pi. The third point is the average of 0 pi and 8 pi, which is how much? 4 pi, yep. The second point is the average of 0 and 4 pi, which is how much? Check. 2. Anything else? Yes, 2 pi. And the fourth is, again, we want everything nicely spaced, so average the third and the fifth, and you get 6 pi. So this time the values worked out very nice. The averages were easy because there was no fractions. Okay, and that's it for the table. Questions on that? Right, so now let's make our sketch. So we've got 0, 2 pi, 4 pi, 6 pi, 8 pi. Now, normal cycle would end right here. That graph that I just drew right there, that's the normal one we've been doing all week. It's all between 0 and 2 pi. Our graph is going to stretch all the way out to 8 pi. It's going to stretch out 4 times as much. So, let's see. Got 1, 0, negative 1, 0, 1. So 1, 1, 0, negative 1, 0, 1. Now, when you look at that, you might think I forgot some labels. What labels didn't I put? Yeah? I didn't put my y's. That's okay. If you don't put labels, I'm always going to assume you're going by ones. That's what you always assume on my graph paper. You always go by ones if you don't put a label. So if you did that graph on the test, that'd be full credit. If you did this graph on the test, that would be 1 out of 2 points for the graph. Because all your graph is right, but this isn't 1, 2, 3, 4, 5. Those are not what the x values should be. So you've got to put them in. Questions on that? All right, so let's look at the last one. So this one is sine of pi over 2x. Now, before I started, what's pi? Like roughly about what? Okay, in degrees it's 180. What is it as like an actual decimal? It's about 3.14. And if you take half of 3.14, you get 1.57. So the number in front of x is about 1.5. A little bit bigger than 1. Not a lot bigger, just a little. So what does that mean? You're going to get a little bit of a compression here. The bigger it is from 1, the more compression you get. 1.5 isn't that big. So it'll compress it a little. Okay, let's see how much. All right, so y's, hopefully by now we know those. First x value should be 0. And now let's figure out where the first cycle ends. Okay, Dan, what's my fraction for where the first cycle is going to end?
Pi over 2.
So what goes in the top? We'll start with that.
So I don't know.
Yeah, sure. Anybody help him out? What? Just the top part. Okay.
2 pi.
2 pi goes in the top. Now, do you remember what goes in the bottom?
2.
So where do we look to get the number that goes in the bottom? Just tell me where the number is. It's in the parentheses. Yep. So what's the number in the parentheses? Pi over 2. So that's what's going to go in the bottom. Now, we've dealt with this before. Instead of dividing by the fraction, what do? Flip it. So make it 2 pi times what? 2 over pi. What does that come out to? 4, right? The pi's are gone, so this graph has a cycle that's 4 units long. No pi in it. 4 radians, if you want to be specific. So it starts at 0, it ends at 4. What's the halfway point? 2, and then the quarter mark is at 1, and the 3/4 mark. 3. So this is the first time we've got such nice points, you don't have to put any labels on your axes. You can go by 1s on the x's and 1s on the y's. That's the only time this week that it ever happened. Why did it happen? Because of that right there. When you flipped and multiplied, it wiped out the pi. Right? So if you did this on the test, 0, 1, 1, 2, 0, 3, negative 1, 4, 0, you get full credit for that graph. That's fine. If you put the labels in, that would also be full credit. Yeah, if you put the wrong labels in, then you'd lose points. Like if you put like 1 pi, 2 pi, 3 pi, 4 pi, no, that's not right. Okay, and that's a period change. So any questions on that? Okay. Okay, so with the time we have left, I have time to show you one of the things we can do with sound. I'm just going to put that up, pause the video here. So the homework is a worksheet. It'll be 5 questions, just like the other couple nights.